Hello everybody and welcome back to more of the 2017 Fermat paper, and we're actually going to finish it off. We're on the very last question, question number 25. So let's take a look. Hopefully you already have. Alright, so what have we got here? Let r equal the square root of 53, and already I'm unhappy. 53 is a very weird number to have here. It's prime, I know that. But, okay, r is root 53 over 2 plus 3 over 2, square rooted. There is a unique triple of positive integers a, b, and c, such that, what have we got here? R to the 100 is equal to 2r to the 98 plus 14r to the 96 plus 11r to the 94 minus r to the 50. Well, that's a bit of a jump. Plus a r to the 46 plus br to the 44 plus cr to the 40. Okay, so we know that's true. There's a unique a, b, and c positive integers that satisfy this weird equation in R. Okay. What is the value of a squared plus b squared plus c squared? Okay. Alright, so first thoughts. I'm probably going to have to figure out a, b, and c. The reason being, if I could just get a squared, b squared, and c squared popping out of this equation from some weird manipulation and my knowledge of R, they wouldn't need to tell me that it's unique or that they're positive integers. So I'm under the impression I will have to figure out a and b and c, and that's going to be kind of hard because we have one equation and three unknowns. Not necessarily impossible because we do know other things about them. They have to be positive integers, for example. Boy, okay. So r is equal to square root of something. Let's copy down what r is and this equation, and we'll see if we have some thoughts on it. So it's quite odd that we've square rooted r. And I don't like the 53 there either. We also have r to the 100 is 2r to the 98, and then I think it was minus 14. I know it was 96 and then 94, and then it makes a weird jump down to 50. And then, is it 58 or 50? Not 58, 48 next? 46, 44, and 40. Okay, 46, 44, and 40. I think it was A, B, and C this way. It doesn't really matter right now. I think this was 11 and this was a minus, but let's double check. So it's plus 14, plus 11, minus, and then everything else was plus. Not bad, not bad. Okay. So this allegedly is satisfied by R. And this is a polynomial. We're told that these guys are integers. Now, first thing I'm noticing here is my powers are all even. Okay, so if I were to create a new, let p be r squared, I could just get rid of this square root sign. So it'll be, we'll still have one square root sign, but then we suddenly have everything sort of reduced. It's p to the 50 is the same as r to the 100. And this is 2p to the 49 plus 14p to the 48 plus 11p to the 47 minus p to the 25 plus a p to the 23 plus b p to the 22 plus c p to the 20. Has this actually helped me in any way? Not yet exactly. So, two things are drawing my attention, and we'll talk about them. One, this is a polynomial, and so I might want to rearrange the whole thing so it looks like something equals 0. because that's really what we're used to a whole lot. I mean, yes, this is a p to the 50s as a degree 50 equation, but what would we do if it was p squared minus 3p plus 10 or whatever? You'd put everything over to one side and equal 0, and you'd use the quadratic formula. Now, there's no degree 50 formula, but my instinct still here is get all the variables onto one side. Actually, I'm looking at it. If I do that, I can take out a factor of p to the 20. So that's at least something. Maybe our goal here is make this degree really, really small and something will pop out. The other thing I'm noticing here, and I don't know if this is something I can use or just some weird artifact of our choice of p, but there is clearly a divide. We have a bunch of powers up here around 50, and then, a bunch of powers in the low 20s. It sort of splits into two. Now, it doesn't actually, split into two, but the powers here, I feel like there's something going on with these powers and something going on with these powers. And, maybe A is 2 and B is 14 and C is 11. And actually, out of curiosity, is that one of the possibilities? So we'd have 2 squared is 4, plus 14 squared 196, plus 11 squared 121. No, that's 321, and the answers, I believe, are ridiculously huge. Okay, so it's not something as simple as it's one equation sort of repeated or something, but yeah, it's catching my eye that these powers are, I mean, I wouldn't bat an eye if this was 45, 43, 42, and 40, but it's not. There's clearly a separation there. Anyway, I don't know what, if anything, I can do with that. That might just be sort of a weird artifact of the question, but I can rearrange the equation. So 50 minus 2p to the 49 plus 14p to the 48 plus 11p to the 47. No, these should be minuses. This will be plus p to the 25 minus ap to the 23 minus bp to the 22 minus cp to the 20 is equal to 0. Alright, and as I say, I can factor out the 20, p to the 20, and we'll get to something a little smaller. So p to the 28 minus 11p to the 27 plus p to the 5 minus... Now, p to the 5, that's a slightly more manageable thing. P to the 3, yeah, we can definitely work with that, minus bp squared. I can certainly work... Actually, squaring p might get rid of the root 53 or something like that. And minus c, and it doesn't have a power of p with it. It's got p to the 0. Alright, so this must be true. Now, p is non-zero. I don't know much about p. I mean, I know what it is exactly. But I know that it's not 0. So p to the 20 is not 0. And that tells me that this equation in here is equal to 0. So I've gone from something that, had a power of 100 down to something involving a power of 30. I'm feeling a little better, a little less scared, a little less intimidated. Although I must confess, I'm a little sort of stuck now. I've done everything I think I can to get this power smaller. Now, once again, this sort of divide between the exponents is still quite pronounced. Stuff near the 30s, and then stuff around... Whoa. And then stuff around the 5 and 3, and, really, really low numbers, stuff around 0, basically. So, what can we do? Well, I feel like everything we did so far has not used P or R at all. I mean, technically, there was no information in P other than that it's R squared that allowed us to do all of this. And I feel like the fact that we've been given the value of P is not something that we can just, dismiss this. I mean, the value of P should definitely affect the sort of shape of the polynomial. It should affect the little a, the little b, and the little c. So what can we learn about P? That's the real challenge now, is what does the actual value of P bring to us? I mean, so we get P is, I'm going to change it to 3 over 2 plus root 53. Actually, I can just change it to 3 plus root 53 over 2. Don't know why they didn't write it that way in the first place. Okay. So, well, I'll tell you what this reminds me of here. This looks like a solution to a quadratic. Okay, if I put this minus sign in here, you'd say, yeah, somebody did the quadratic formula. Now, if I did have the minus sign there, root 53 is definitely bigger than 3, so you'd get a negative value for P, and you wouldn't be able to square root it here. So, P is definitely the root of a quadratic, and it's the positive. We chose the plus, not the minus. Can I figure out what that quadratic is? Because the observation that this is a solution to a quadratic, I mean, we've got P as the solution to a degree 30 equation, and P is the solution to a degree 2 equation. There might be something there. And in fact, for those of you who know some more advanced math, you know that there definitely is going to be something there. We can get the quadratic of P, the quadratic that P is the solution to, and that's going to have to be what is called the minimum or minimal polynomial of P. Every other polynomial that P satisfies, it can be evenly divided by the minimum polynomial. So I might choose to use this fact, although I don't want to, because I think that's a little more advanced than, well, it's Fermat 25. But yeah, so we do know that this is at least the solution to a quadratic. Let's figure out what that quadratic is. So we could do some observation that it's going to be negative b plus or minus square root of b squared, blah, blah, blah. Is that the easiest way to do this? Because then we're going to have, a is going to have to be 1. I'll change it to this, so we don't get confused with the little a and the little b and so forth. So b would have to be negative 3, a would have to be 1, and b squared minus 4ac would have to be 53. So that'd be 9 minus 4c would have to be 53. So c is going to have to be negative as well. Bring the 9 over to the other side. Negative 44. C is 11. Oh, no, it's not negative 44. It's regular. It's just 44. C is going to be negative 11. Yeah. Yeah. So P satisfies P squared minus 3P minus 11 equals 0. Okay. So I'm going to try and avoid using the higher math that I know that that quadratic has to divide this thing. And see if I can do this a normal high schooler way. So Okay. P squared minus 3. I can bring that over to the other side. I can say that this is 3p plus 11. So this gives us a way to translate higher powers of p into smaller powers of p. I'll show you what I mean. P cubed is just p times p squared. Well, I know what p squared is, so this is 3p squared plus 11p. But p squared is, once again, 3p plus 11. So now we get 9p plus 11p, 20p plus 33. And so now we've got p cubed, but it's in smaller terms as well. And, we can do the same thing with p to the 4. And p squared and p to the 4 are in my polynomial. So maybe there's a pattern here I can notice. So this is p to the p cubed, so that's going to be 20p squared plus 33p. So that's 20 times 3p plus 11 plus 33p. So that's 60, so that's going to be 93p plus 20 times 11 is 220. So we go 3 to 20 to 93. If p to the k is equal to, what are some good variables? Xp plus y, let's say. We haven't used x or y at all. I was going to use a little a and a little b, or a p or a q and an r, but some of those are taken. Then p to the k plus 1 is equal to xp squared plus yp, and that's going to be x times 3p plus 11 plus yp. So it's going to be 3x plus yp plus 11 times x. And then we could repeat this process again and again and again. Does this especially help me? I think the numbers are going to get too big. I know p to the 5 is in our equation, so let's at least do that one, but now I don't have to keep expanding everything out. 3 times 93 plus 220. I'm actually having to grab my calculator for this. This makes me think this might not be the best way to do the question. 499 and then plus 11 times 93. 1023. So those are some bigger numbers. Now, I could go ahead and compute p to the 6 this way, and p to the 7, p to the 8. And if I had time, I could get all the way up to p30, and then I'd be able to express that p to the 30 minus 2p to the 29, all in terms of a p and a p to the 1 and a p to the 0, or p and a constant. And then I'd know that has to be equal to 0. And there'd be an a, a b, and a c in there, and I guess... I mean, that's still one equation and 3 unknowns. So, what to do? Well, let's go back and stare at our original equation here. If worse comes to worse, I will just straight up divide this polynomial by the quadratic, and I don't think that's entirely unreasonable, but you kind of need to know about minimum polynomials to do that. The thing that... It's really odd that the powers jump here. Something's got to be up with those powers jumping like that. So I'm going to try something. P to the 30 minus P to the 29. Now I don't actually, I haven't worked out what those values are in terms of the, what's in front of the P, what are the X, P plus Y's for each of these. I don't have those. But there's such a gap between these exponents and the 5s. that I feel compelled just to look at this on its own. Now, I don't know, for example, that this equals 0 or something. If it did, that would be amazing, and it would just knock everything away. But I can take out the 27, and then I'm left with p cubed minus 2p squared minus 11p minus 14. And these are smaller values that I have computed on the other page. And I just want to double check that I did copy this correctly. Yeah, did I have the 11 first or the 14? So it was 11 and then 14, and now I genuinely can't remember. Do I need the 14 first? Oh, wait. Okay, 14 and then 11 is what we need. 14, then 11. 14, then 11. 14, then 11. And we didn't have it. So 14 and then 11. And then 11. All right. All of that's fine. So once again, if the p to the 27, I mean, I know that's not 0, but if this part is 0, then that would mean that the sort of the first half of the polynomial is irrelevant. And we can just focus on the p to the 5, p to the 3, which are much simpler values. So I'm really, really hoping here. I imagine it probably is, but I don't know for sure. Now, I do know p cubed minus 2p squared minus 14p minus 11. That's the same as, and we just worked this out, p cubed was 20p plus, it wasn't 11, was it? Well, let's just flip the page and find out. 20p plus 33, that's what it was. So 20p plus 33 minus 2 times 3p plus 11 minus 14p minus 11. 20p plus 33 minus 6p, ooh, that's promising, minus 22 minus 14p minus 11, but 33 minus 22 minus 11, 0. And then 20p minus 6p minus 14p, that's 0p. So yeah, the whole first half of the polynomial is irrelevant. Oh, that's nice. And that really just came about because I noticed that seemed kind of odd to have such a gap. Okay, and then it's minus c equals 0. I think that's it. But now I can ignore this first half. And it's p to the 5 minus ap cubed minus bp squared minus c. Okay. So, rather happily now, I have, that's gone. And so now this is just p to the 5 minus ap cubed minus bp squared minus c equals 0. And I can do the exact same thing. And I did work out p to the 5, right? Yeah, p to the 5, 499p plus 1023. And this is where it's getting weird. I just am going to have one equation and 3 unknowns, so it's still a little odd. But we'll go with it. 20p plus 33 minus b 3p plus 11 minus c is equal to 0. Okay, so if I group like terms, I have 499 minus 20a minus 3b p is equal to 0. And 1023 minus 33a minus 11b minus c is equal to 0. Okay. So this has to be true. Now, for this to be the case, P is a quadratic. So A, B, and C are integers. So we get integer times P minus integer times integer times P minus integer. So if I rearrange this, I get P. So P. If they're not 0, we can rearrange and say P is 33A plus 11B plus C minus 1023 over 499 minus 20A minus 3B, and that would be rational. But that can't happen because in my expression for P, I have a root 53. Okay, and that's 53 is prime, square root of that, definitely not rational. So we've got a problem. Okay, if A, B, and C are integers, I could rearrange this equation and get P equals, some integer over some integer. I'd get a rational expression for P. That's not allowed. So what does that tell me? It tells me I can't do this rearrangement. What's stopping me? Dividing by 499 minus 20A minus 3B is stopping me. If that were 0, I couldn't do this division. But if we've got 0 times P plus an integer is equal to 0, well, that's just that integer equals 0. So, because I know P is irrational, so we'll say, but P is irrational. P is 3 plus root 53 over 2. That is not a rational expression. So that tells me that 499 minus 20A minus 3B must be equal to 0. Otherwise, I could divide by it and get a rational expression for P. And that also then tells me that 1023 minus 11A minus... Was it 11A? No, I think it's minus 33A minus 11B minus C is equal to 0. Let's just double check that. So the fact that A, B, and C were integers has helped me here. Yes, it was 33A. So we've used that fact. We might even have to use the fact that they're positive integers. Now at least I have 2 equations and 3 unknowns, so that's some kind of progress. And the fact that they're positive integers makes me think that there's only going to be so many solutions here. Alright, so the whole question has now fallen down to, can I work out these? A unique A, B, and C being positive integers from here. Well, C is only in this second equation, so we'll say C is 1023 minus 33A minus 11B. Now, 11 and 33, they catch my eye. They're multiples of 11. And so is 1023, because that was 93 times 11. So that tells me 11 has to divide C. Okay, so that's, so if they're positive integers, we have to have, alright, so C is positive. So that means 33A plus 11B must be less than 1023. And that sort of limits what C can be. Can C be 1 times 11 or 2 times 11 and so on? Now, I do know exactly that 20A plus 3B has to be equal to 499. Where can we go from here? Geez. Okay. Can I get a solution to this? So this equation right here, the one equal to 499, I think I can generate some possible A's and B's that'll work, and then which of those give me positive C values, I guess? Maybe? Okay, so what's a really stupid and obvious solution to this? If b is 3, we can get rid of the 9, but then we got 490, which is not a multiple of 20. A equal 20 will knock off 400, and then b equal to 33 will do just nicely. And then I can... So 20 and 3 have a GCD of 1. So if I want another solution, I can add 3 to 20 and subtract 20 from 33. So the 20 and the 3 coming from here. So I think that would work. So how about 20? Get out the calculator. 20 times 23 plus 3 times 13. Yeah, that works. And we can do the reverse direction as well. We can add 20 to each of these. So we'll put this in the middle. So I can lower this by 20. I can increase this by 20 as well. And then we're going to get b is 93. But if b is 93, notice that then this part here would be exactly equal to 1023. And if I go any lower with the 13s, I'm going to get b is negative. So if I get 13 minus 20 would be negative 7. That b has to be positive. So a could be 23, or we could have a is 17, or a is 14, or a is 11. But this one I'm saying won't work, because then when we'd have 1023 minus 1023, c would be less than 0. So we have 4 possibilities. Let's just figure out what their what c value we get. Okay. Each of these has a being positive, b being positive. Only one of them should get me c being positive. Which one? No idea. We'll start at the top. 23 times 33 plus 11 times 13. It's going to be 902. Subtract that from 1023. We're going to get 121. Well, that's positive. What if I had a is 20? 20 times 33 plus 11 times 33. That's going to be exactly 1023, and that's going to give me c as 0, so that's not going to work. And I imagine the other ones, it's just going to, the b value is just getting too big. But we'll do one more just to make sure. 11 times 53. Yeah, 1144. And we're going to get c is then negative 121. And I imagine the next one would be negative 242. But it doesn't really matter. We have a solution with a, b, and c being positive. They told us it's unique, so this is what we're going to work with. And what do we want? We want a squared plus b squared is plus c squared. And that's going to be 23 squared plus 13 squared plus 121 squared. Is that going to be big enough? Because I noticed the answers are in like the tens of thousands. So 13 squared. And then 121 squared. So I'm getting an answer of 15,339. Is that one of the possibilities? Yes, D. Okay. So D is our answer. We did happen to work out the A, B, and C immediately. And that wasn't so bad, but I mean, if you didn't make the observation that, gee, these powers of P are drastically different on one half of the equation than the other, I'm not entirely sure what you would do. So we've got our answer of D. What I'm going to do for the next little part of the video is I'm going to explore what would have happened if I'd used my higher math that I'd learned in university. The only reason I was not using it is because I didn't learn it in high school. And there's not a lot of sense in me showing you something that's beyond high school level math to solve these problems, because it's not something that you'd be expected to do. There's always a non-high school solution. Or sorry, there's always a high school level solution. So at least that's what I think I've got here. But I'm going to try and do this with my knowledge of minimum polynomials. And I'll see what, if anything, I can do. And, maybe I'll just reduce it down to a situation that I already had. But, so this is just me going a little further. If not, I'll say it now. If you don't want to join me for the exploration of the minimum polynomial, I'll just say my usual thank you for watching. I hope you liked this question and the contest itself. I certainly did. It was an interesting contest to go through. And so this is the Fermat 2017. The next thing from 2017 would be the Hypatia. But no matter what video you watch, I will see you guys then. Have yourself a wonderful day. Okay, let's. If you're sticking around, let's do minimum polynomials. Okay, so I know p squared minus 3p plus minus 11 is the minimum or minimal polynomial of p. As I mentioned before, p is not rational, so it's not going to be something like 10p minus 8 or something like that. So the next smallest you could get is a quadratic, and since this has 1 for its leading coefficient, this is what we call a minimum polynomial. So in general, if you've got if we've got x cubed minus 1 equals 0, I know x equals 1 is a solution. And hey, here I've got another equation where x cubed minus 1 is equal to 0. X squared minus 1 equals 0 also has x equals 1 a solution. But just because we have that doesn't mean that one polynomial is a factor of the other. That's not always true. But if you have the minimum polynomial, the smallest degree polynomial that you can have, which in this case for x equals 1 is x minus 1, any other polynomial where x equals 1 is a solution will have x minus 1 as a factor. Okay? So, if this is the minimum polynomial, then that tells me that p squared minus 3p minus 11 divides my p to the 30 minus 2p to the 29 minus 14, then 11, I think it was, plus p to the 5 minus ap cubed minus bp squared minus c. It has to. We know that this is equal to 0 when I plug p in, and I know this is equal to 0, and it's the minimum polynomial. So we know this is true. So I think what I'm going to do is I'm going to do some polynomial division. And based on what we learned, I should get that it definitely, everything factors out nicely and neatly for the first half of it. But we'll come to that in a moment. And this will just be an exercise in polynomial division. Alright, so p squared goes in p to the 28 times. And then we multiply p to the 28 minus 3p to the 29 minus 11p to the 28. And we subtract, p to the 28 times p squared is p to the 30. So that'll get me p to the 29 minus 3p to the 28 minus 11p to the 27. And then, oh, look at that, p to the 27 goes into that evenly. So we stop there. And then, so we can ignore that first half. And then that would be, right now we've got the observation that, oh, the first half is already equal to 0. So now p squared divides into p to the 5, p to the 3 times. and then p cubed times, I guess technically we need to have plus 0 p to the 4 minus a p to the 3 minus b p squared plus 0 p minus c. There, we've got everything covered. P to the 5, and then minus 3p to the 4 minus 11p to the 3. I'm running out of room. I'm just going to ignore the first half and polynomial divide everything starting with the p to the 5. Alright, p to the 5 plus 0p to the 4. It's important to have your placeholders with the 0 coefficients. Minus a p cubed minus b p squared plus 0p minus c. So, as I say, p cubed divides in, so we get p to the 5 minus 3p to the 4 minus 11p cubed. So we've got 3p to the 4, and then plus 11 minus a p cubed. Don't know exactly where we're going with that, but that's okay. We bring down the minus b p squared. P squared divides into p to the 4, 3p to the 4 plus 3p squared many times. And it'll be minus 9p cubed, and then minus 33p squared. Those will cancel, and we will be left with 20 minus a p cubed minus plus 33 minus b p squared. And then we'll bring down the 0p. And now p squared, so we're going to get 20 minus a p. Doesn't really matter, don't worry too much about that. And minus 3 minus 3 times, so minus 60 minus 3a p squared. I'm not exactly happy with how this is turning out, but that's okay. And then minus 11 times this. So minus 220 minus 11a p. Alright, so those ones cancel, and we've got, so it's minus 60, so this will be 93 plus, no, 93 minus 3a minus b. P squared. And so it'll be plus 220 minus 11a times p, and then we bring down the minus c, and this should divide evenly. So this will be plus 93 minus 3a minus b, and we'll get the exact same thing here. And then it'll be plus, or it'll be minus 3 times that, so it'll be minus 3 times 93 is, oh gosh, 3 times 93 is 279 minus 9a plus, no, minus 3b. And then minus 11 times that, and that'll be 1023 minus 33a minus 11b. And this should be equal to 0, but when we do the subtraction, we get 499 minus 20a minus 3b times p plus 1023 minus 33a minus 11b minus c equals 0, and we're right back to where we were. So minimum polynomials didn't actually help me out a whole lot. But it would have helped me identify that the first half of the polynomial is sort of separate from the p to the 5, p to the 3 stuff. Which, admittedly, I only found sort of on a hunch that, gee, wow, these exponents look kind of weird, that they sort of have nothing to do with each other. Which is not always the case. I mean, you can get some very weird minimum polynomials, but certainly not on a Fermat question. Yeah, so that's really all my knowledge of minimum polynomials did. We get the same expression that we need to work with. P is not rational, so both of those coefficients have to be equal to 0. We're back to where we were a little while ago. So, yeah, didn't blow the question out of the water, which sometimes university level math can do on a contest like this, but no. So, as I said before, we're all done the 2017 Fermat paper. Let me know how well you did on the paper for this year, if you want to, or if you had a different way of doing this question. And I will see you for more 2017 papers in the future. Thanks for watching.